Okay, welcome back. Today we're going to continue talking about functions, and in particular, we'll talk about injections, surjections, and bijections. Uh, but let me just remind you of our definition of a function, or one of our definitions of a function from last time. So we said that a function f from a to b is a rule that assigns to each element of a exactly one element, which we call f of a in B. So you can think of a function as a domain, a codomain, and a rule that tells you what the function does to each element of A. It spits out one element of B. This is one way to think of what a function is, but here's another way to think about what a function is. You can also think of a function f from A to B as a certain subset of the Cartesian product A cross B. Well, which one? Here's what I'll do. Let's say that f is defined to be this specific subset of the Cartesian product. So you take a f of a, where a is an a, and you look at this subset of a cross b. Okay, so if you have a rule, I mean, you have a function defined by a rule, which means that you can take any element a and plug into f, and you get an element of b. You can look at all ordered pairs where you take something from a, plug into f, that gives you something from b, and so this gives you an ordered pair of elements, one from a, one from b. So that's an element of the Cartesian product. Okay, so here I'm using the same letter f to refer to two things. So this, sometimes mathematicians will call this abusing notation. To abuse notation means that really you should only use one name for one thing, but to abuse notation means I'll use the same name for two different things. So here, by abusive notation, we use f to mean both the rule that takes a and maps it to this element f of a, and this subset of a cross b. Okay, those are two different things. A rule is one thing, and a subset of a Cartesian product is another thing. However, they're really equivalent concepts. It turns out that given a rule, you can get a subset of a cross b, and given a special subset of a cross b, you can get a rule. And so even though these are different things, you can translate between one and the other, so it's okay to call both of them the same name. So I said a certain subset. Of course, in order to be a function, you need to be a certain subset. So let's think back to our function from last time, right? So I said sometimes when you think about the definitions for functions, it's good to draw some small example. So our example from last time looked like this, right? We had a domain with 4 elements in it, which I called A1, A2, A3, and A4. We had a codomain with 3 elements in it, B1, B2, B3. And I said, okay, imagine the rule that maps A1 to B2, which I'll draw with an arrow here. It maps A2 to B1. If that arrow would end at B1, that'd be good. And I think it also mapped A3 and A4 also to B2, right? So you can think of this as the rule that takes A1 to B2 and the rest of them to, sorry, A2 to B1 and then A3 and A4 to B2. So this is thinking of it as a rule. Well, which subset of A cross B is F? Well, it's supposed to consist of ordered pairs where the first element is an element of A, and the second coordinate is f of A. So in this case, you could consider the subset A1 comma B2, because that's this element of A and F of it. It's also A2 contains A2 comma B1, A3 comma B2, and A4 comma B2. And this is a subset of A cross B, which we could call F, right? Because this subset of A cross B contains all of the same information as the rule. If you want to know what the rule does to A1, you just look at the subset of A cross B. A1 appears only in one of the elements. And then to figure out what f of A is, you just look at the other coordinate of that element. Okay, this is, by the way, a proper subset. So one way to notate, okay, so this is a subset, but it's actually a proper subset. It's not equal, right? Because this thing does not contain A1 comma B1, for example. So that's how you go from a rule to a subset. One question you could ask is, well, which subsets can actually come from functions? Well, if you think about it, the thing that made this arrow diagram, the thing that made this a function was that we had one arrow out of every element in A. That's what made it a function. It didn't matter that there wasn't an arrow into every element of B. It didn't matter that some elements of B had more than one arrow in. What made it a function was that there was one arrow out of every element in A. If we think about what this means on the Cartesian product side, it means that each element of A needs to appear once and only once as a first coordinate of an element of the subset. So each element of, let's do this different color, each element of A appears exactly once as a first coordinate. So if you have a subset of A cross B that has that property, then that will define a function, right? Because that will say exactly what the rule will do to each element of A. And there's no ambiguity because you only have A1 appearing once, right? If you also had like A1 comma B1 in this subset, this wouldn't be a function because there'd be some ambiguity as what happens to A1. Does it go to B1 or does it go to B2? Which means that it wouldn't be a function. If on the other hand, if we were missing, right, if you imagine that we were missing this element from our subset, that also would not be a function because you wouldn't know what to do to A1. So if you can think of a function as a subset of the Cartesian product such that each element of A appears exactly once as a first coordinate of an element in the subset. Okay, that's another way to define what a function is. Okay, now somehow this seems like a little bit of a weird way to think about what a function is, right? To me, anyways, it's much more natural to think of a function as a rule. Why am I just throwing this weird subset of the Cartesian product at you? It turns out that actually you've been doing this for a very long time. So this actually isn't so weird. Because let me consider my favorite function, the function from the reals to the reals given by g of x equals x squared. By the way, I'm not sure if I remember to say this last time, but another way that you might see this notated, so this is one notation. Another way you might see this notated is like this. G is a function from R to R that sends x to x squared. So these two mean the same thing. This says the name of the function is g, it's a function from R to R, and the rule takes any element x to its square. And if you're following along LaTeX, this is / maps to. I wonder if I talked about this last time. My memory's going. It happens when you get old. Anyway, one thing that probably you're very familiar with if I tell you this function is the graph of the function. And you would all very happily say, oh yes, this is the graph of the function g of x equals x squared, right? Well, what is a graph? here what you've done is this line represents R, this line represents R, and as we talked about last time, the whole plane represents the Cartesian product R cross R. And what you've done is you've picked a bunch of points in this Cartesian product, and you've called this the graph of G. Right? What's on this 0, 0, that's in your graph, 1, 1, like 2, 4, -3, 9. Why are they on your graph? 0, 0 is on your graph since G of 0 equals 0, right? -3, 9 is on G since G of -3 equals 9. So this subset of the Cartesian product definition of a function is exactly what you're drawing when you draw the graph of a function. You're drawing the subset of R cross R that contains all the points x comma g of x. So whenever you draw a graph, it's like picturing the function as a subset of the Cartesian product of the domain cross the codomain. So we could also draw a graph of this function, except the domain only has 4 elements in it and the codomain only has 3 elements in it. So maybe I could draw it like this, right? So I'm drawing these lines here, but let's say there's just A1, A2, A3, A4. Those are my 4 elements of my domain. I have 3 elements of my codomain, B1, B2, B3. Maybe I should draw these with hash marks rather than dots. I probably also shouldn't even put an arrow tip here, right? Because there's no sense in which this goes on forever. Just these 3 elements. And then A1 mapped to B2, A2 mapped to B1, A3 and A4 mapped to B2 as well. So you can think of these 4 points in this invisible grid, right? Really, this is a grid consisting of 12 points. It's not the whole plane. It's just these 12 points, and the function is like these 4 points. It's these 4 elements of the Cartesian product. Right? And one thing you learned even way back in elementary school is that you can tell whether you've drawn the graph of a function if it passes the vertical line test, right? So this function is a graph of a function because it passes the vertical line test. What is the vertical line test really saying? It's saying for each element on the x-axis, your function passes through one and only one place in the graph of a function. That means for every input to your function, you get one and only one output, right? And this function also passes the vertical line test where we can only draw 4 possible vertical lines here. This graph intersects every vertical line once and only once. That means it's a function from the domain to the codomain. It's just in this case, the domain has 4 points in it and the codomain has 3 points in it. Okay. Now what we're going to move on to is we're going to study specific properties that a function might have. In particular, we're going to talk about what it means for a function to be an injection, a surjection, or a bijection. And I know that you covered this in Math 308 because, again, this part of my notes, I've basically just copied and pasted from when I taught Math 308. So it's probably none of you took it with me because it's now been a while since I taught 308, but maybe you did. Wow, why is this? Where are my lines? I need my lines. There we go. Actually, for this, no. Okay. So this is really where 6.3 actually starts. Okay, so here's your first definition. A function f from a to b is called injective if for each little b in b, there exists at most 1 A and A such that f of A equals B. Okay, so an injective function is one such that for every element of the codomain, there's at most one element of the domain that maps over to it. In other words, there's either one element of the domain that maps over to it or no elements of the domain that map over to it. So I'm going to leave some space here because I'm going to write something different underneath. But what does it mean to be an injection or an injective function? What it means is if I look at the codomain, each of these needs to have only one arrow going into it. There can only be at most one thing mapping over to it in the domain. So maybe something like this. But I might have some other dots here, right? There's at most one thing mapping over to it. I still can only map one arrow out of these guys because it's going to be a function. But to be an injective function means that you can only map one arrow into any particular dot, maybe more than one. Sorry, maybe none. Another way to say this is that if you take different elements from the domain, they have to map over to different elements in the codomain. They could never map over to the same element, because if they mapped over to the same element, then you would have more than one A and A mapping over to a specific B. So here's other ways to phrase the condition. So one way that you can say it is exactly what I just said. If you have different elements of the domain, they must map over to different elements of the codomain. So if x is not equal to y, okay, let's say for x, y, and a, so given two elements of your domain, if they're different, then they must map to different places. If x is not equal to y, then f of x is not equal to f of y. This is one way to phrase the injective condition. Another way to phrase it is to take the contrapositive. So another way to phrase this is to say for x, y, and a, if f of x equals f of y, then x equals y. What is this saying? This is saying if two elements map over to the same thing over here, if two elements map over to this dot, well, they must actually have been the same element to begin with. I can never map two different things over to the same thing. Okay, so an injective function is one that never maps two different things to the same thing. So an injective map is like something that doesn't collapse elements together. That's the idea. So an injective function never maps two different things to the same thing. Where by thing here, I mean element of the domain or element of the codomain. Okay, so just some more things to know. An injective function is sometimes said to be one-to-one. And I think this is the phraseology that's used in Math 308, but personally, I think injective sounds better than one-to-one. So I will almost always say injective function, or the noun form is, it's sometimes called an injection. Okay, so you might say something like, suppose f from A to B is an injection, that means it's an injective function. Okay, so I guess I owe you some examples where we can think about injectiveness. Right, so we're used to examples from calculus. So, man, this is annoying. I wonder what I've done here to make OneNote annoyed. We're used to thinking about functions from calculus, so let's do that. Actually, first, let's think about this small example, this function f from A to B from before, where A had 4 elements and B had 3 elements. This function is clearly not an injection because it has more than one element mapping to the same element. Right, so F was not an injection, since F of A1 equaled F of A3, which was B2. Right, so A1 and A3 were different, but they mapped over to the same thing, so it violated any of these equivalent ways of thinking about an injective function. There were two different things that mapped to the same thing, or they had the same image, but they were different, so they would fail to satisfy being injective. Okay, now let's consider the function, my favorite function, g of x equals x squared. Is this function injective? Well, no, is not injective. Why? Because this function does sometimes map two different things to the same thing. G of -1 equals g of 1. Those are both 1, but 1 does not equal -1. So we took two different inputs and got the same output. Another way that you could see this is from the graph of the function. Right? What does it mean to not be injective? To be not be injective means that there's some output that has more than one input that maps over to it. In other words, if you draw the horizontal line at this output, let's say that this output is 1, there's two different inputs that map over to it, -1 and 1. So since this horizontal line intersects the function in more than one point, the function is not injective. Okay, some more examples. We could let h from R to R be given by h of x equals e to the x. I could let j from R to R be given by j of x equals sine x. Let's let k from R to R just be the constant function 2. And let's let L from R to R be the function L of x equals log x. Okay, so since you're familiar with these functions from calculus, I want you to think about whether or not they are injective. Okay, so pause the video, do that. So this function, e to the x, if we think about what its graph looks like, we can get some idea. Its graph looks like this. Right? This graph is always increasing. You can prove that by taking a derivative test or something. Which means that if x and y are different values, then e to the y is, e to the y and e to the x are different. If y is bigger than x, then e to the y is bigger than e to the x. In other words, every horizontal line passes through this function only once. So this function is injective. If x doesn't equal y, then e to the x doesn't equal e to the y. Right. Okay, for sine of x, this function is very not injective. It's sort of like every point in the range is hit infinitely many times. Right? J of 0 equals j of pi equals j of 2 pi. These things are all 0, right? Because the function looks like this. So if you want to get the output 0, there's infinitely many ways to do it, which means there's more than one way to do it, so it's not injective. Even worse than that is the constant function. This is extremely not injective, right? K of any number equals k of any other number equals 2. Maps every real number to the same real number. So this is like the furthest you can possibly be from being injective. And the log, this one is injective. Again, we can think about this from the graph, right? I realize I've made a mistake here, right? L is actually not defined from R to R. someone should have told me this as I'm lecturing asynchronously. It's only defined on positive real numbers, so I can write it like this. I don't think anybody the last quarter I taught this told me either, otherwise I would have fixed it in my notes. Okay, so that's what an injective function is. It's the same thing as a one-to-one function that you learned about in linear algebra. And you also might remember that there's a counterpart, which is a different thing. Which is the following definition. So a function f from a to b is called surjective if for each b in the codomain there exists an element a in the domain such that f of a equals b. Okay, again, I'll leave some room, but let's think about this in terms of arrow diagrams just to get some idea. This is a and this is b. This is saying for every element, for every dot on the right side, for every element of the codomain, there is some element in the domain that maps over to it. There could be more than one, but there's definitely not zero. What does that mean? It means that every dot has at least one arrow in. Another way to say this is that every single possible output is actually the output of the function. So it says that there's maybe more than one arrow in, but there's at least one arrow in for every dot. So what is this saying? This is saying that the function f hits the entire codomain. The entire codomain gets hit by this function f. So another way to say this is that the range of f is equal to the codomain of f. Right? Remember, the range is all the things that the function actually hits. That is equal to the entire codomain. Everything gets hit by the function. Okay, and a surjective function is sometimes called onto. An onto function, although I really don't like the word onto to describe this. I think surjective is a much better word. Onto just sounds grammatically awkward when you use it correctly in a sentence. If you say this function is onto, I think that's a horrible way to say that the function is surjective. And a surjective function is called a surjection. So here, this function f that I've drawn is a surjection or a surjective function. Okay, by the way, how do you show? I wonder if this is a proof technique later. I actually kind of forget. How to show if a function is injective or surjective. Let's just put it here because while I remember it. So for injective, you essentially just use the definition. So you can say maybe, suppose f of x equals f of y, and show that x equals y. Or you can suppose that x does not equal y, and show that f of x equals y, f of y. I think the first one is generally a bit more powerful because two elements being equal is a very strong statement. I think that's the easier direction of the contrapositive. How do you show that it's surjective? Remember, surjective means that you hit every element of the codomain. So what you do here is you choose an arbitrary b in the codomain. And what you can do is you can just construct an element of the domain that maps over to it. Okay, you pick an arbitrary element, you find an element that maps over to it. That shows that every element gets mapped to. Right? I guess I should say how to show that it's not surjective or how to show that it's not injective. Okay, so if you want to show that's not, maybe I'll put this in red, injective, what you do is you just produce two non-equal elements such that f of x equals f of y. So a single counterexample works here, right? If you have two different elements mapping over to the same element, that's bad. That's not injective. To set a function is not surjective, you just need to give, find a b and b such that there is no a, such that f of a equals b. So this would require a proof, right? So basically the only thing that you can show by counterexample, essentially, I mean, okay, technically this would be a counterexample if you just produce a single element, but you need to prove that nothing maps over to it. And for injective, a counterexample is just a pair of elements that are different that map over to the same element, which is how we showed that some of those functions were not injective on the previous slide. Okay, what happens if I add a page here? Oh, man. Okay. So some examples. Maybe we'll take the same examples as before. So again, f, the function for before. I guess I called it 1 before, so let's call it 1. 2 was g from r to r given by g of x equals x squared. As I write these down, maybe you can start thinking about whether they're surjective. H from r to r given by h of x equals e to the x. J from r to r given by j of x equals sine x. K from r to r given by k of x equals 2. And L from r to r, sorry, r greater than 0 to r given by L of x equals log x. Okay, so pause the video here and figure out if these functions are surjective or not. Okay, so the first function we drew way back when. This function is not surjective because there's something in the codomain that doesn't get hit. B3 is not ever the output of this function. Right, so this is not surjective. For B3, there does not exist any x in A such that f of x equals B3. Nothing maps over to B3, you can just tell that from the picture. Okay, what about this function x squared? This is also not surjective because there does not exist any x in R such that g of x equals -1. Nothing maps over to -1, right? If you look at this graph of this function, you look at -1, it doesn't intersect the graph of this function. This means that -1 never occurs as an output to the function. Okay, of course, you could change the codomain of the function to make this thing surjective if you want. You could also change the domain to make it injective if you want. So let's actually talk about that after I've discussed the rest of these examples. Okay, h of x equals e to the x is again not surjective because the graph looked like this. In particular, if you take e to any number, you never get out a negative number. You also never get out 0, right? There does not exist any x in R such that e to the x equals 0 or any negative. Right? E to the x is always positive no matter what x is. If x is a real number. Okay, sine of x, also not, because let's state this in a different way. The range of sine of x is just the closed interval from -1 to 1, which is not equal to R. Here's another way to say that it's not surjective. The range is not everything. the range is not equal to its codomain. Same thing with this constant function, because the range is just the set 2. This function only ever outputs one thing. There's only one element in the image of this function. And so the range is just the singleton set 2, which again is not equal to the codomain, which is R. Okay, but this last one, log, this one is surjective. Finally. Why is this? Because the graph of the function looks like this, which means that every horizontal line passes through this function. That means every possible output occurs. And how do we prove it? Let's let y be in R. This is y. I just need to find some element that maps over to it. And there's only one element that maps over to it, namely e to the y. So let y be in R. Then e to the y is also a real number. And L of e to the y equals y. Look, let's say equals log. Log of e to the y, which is equal to y. So this shows that given an arbitrary element of the codomain, I should say r greater than 0. Given an arbitrary element of the codomain, there exists an element of the domain that maps over to it. So this is a proof that log is surjective. Every element occurs as an output. Give me any output you want. I'll tell you exactly what input gives me that output. Okay. I said we could change these functions to make them surjective. Indeed, we could change these functions to make them injective too. But by changing the functions, you are actually changing the functions, so they're different functions. So this function, this x squared function, I could make, let's call this something different because it's not g. Let's call it g2. If I change the codomain to all non-negative real numbers, and I kept the rule the same, this one is surjective. Because now the range is equal to the codomain. I changed the codomain to just equal the range. However, this is a different function because it's a different codomain. This is why the domain and the codomain are part of the definition of a function. G is not surjective. G2 is surjective. They have different properties. They're different functions. Okay, I can also make it injective. By make it injective, I mean I can cook up a different function. I can make G3, and I could just take, say, the non-negative reals. Oh my gosh. Sorry. I don't know what this looks like to you, but my OneNote just crashed. But it's back. I could define a new function, G3, from, say, just the non-negative reals to the real numbers defined by G3 of x equals x squared. This function would be injective, but not surjective. But again, it's a different function. Okay, and then the last definition for today is the definition of a bijection. So a function f from a to b is called bijective if it is both injective and surjective. A bijective function is sometimes called a one-to-one correspondence. Bijective function is sometimes called a one-to-one correspondence. Again, I don't really like this term. I prefer the term bijective function. Which is also sometimes called a bijection, which I do like. F is a bijection. Okay, now functions can be injective or surjective or both. They could be bijective or they could be neither. They could be one and not the other. So a good thing to try right now is to take a few minutes and say I want to draw a function that's injective but not surjective, surjective but not injective, both injective and surjective, and neither. So see if you can complete this table with a small arrow diagram of a function that has or does not have the specific properties. So pause the video here and do that. Maybe if I close some other things, OneNote will be happier with me. Okay, so hopefully what you came up with, let's try to write down a minimal example, right? So if I were lecturing in person, I would ask you to maybe come up to the board and draw it. No such luck. So not injective, not surjective. Let's start at the bottom corner here. So if I want to be not injective, I should map two elements to the same element. And if I want to be not surjective, I don't want to hit the entire codomain. So I think this is the minimal example to find a function that's not injective and not surjective. Okay, if I want to be not injective, but I do want to be surjective, it means that I want to map two different elements to the same element. I want to collapse something. And also, I want to hit every element of the codomain. So this is a minimal example, but let's just add another dot just to spice up the picture a little bit. So to make it clear that you're hitting everything on the right-hand side, but some things are hitting more than once. So that's surjective, but not injective. You can also be injective, but not surjective. So to be injective, I need to send every dot to a distinct dot. But to be not surjective, I don't want to hit everything, so I need to put some lone dot or more on its own. And to be injective and surjective, every dot needs to have one arrow going into it and only one arrow going into it. And of course, you need only one arrow going out of each arrow on the left. So an injective and surjective function or a bijective function will look like this. Okay. So hopefully you can come up with this picture, which shows in sort of very small examples that you can have any combination of being injective or surjective or not. Right? Now let's think of some more functions just to continue thinking about injectivity and surjectivity and bijectivity. So more examples. So let's determine if the following functions are injective or surjective or bijective. Okay, so first two examples are going to be kind of interesting. So for the first two examples, let's let Z5, Z sub 5, denote the set 0, 1, 2, 3, 4. So it has 5 elements with operations plus and times happening modulo 5. Okay, so this is called the ring of integers modulo 5. What do I mean by this? I mean, here's my set. It has 5 elements in it. And if I want to add 2 elements, if I take like 2 plus 4, I should take that sum modulo 5. So it's actually equal to 1 inside of Z5. Right? So if you take the result modulo 5, you end up back inside the set. And so I can think about this set as having a plus and a times operation on it, right? 2 times 4 equals 3 inside of Z5. That's what I mean by Z5. Okay, so let's define some functions. So let's take a function f from Z5 to Z5, given by f of x equals x squared, to a function g from Z5 to Z5, given by g of x equals x cubed. And then 3, maybe I should give a little bit more room. Let's get back to reality, as Eminem would say. Let's take a function r squared to r squared given by h of xy equals x plus y, x minus y. Okay, let me just make a note here that technically my notation here is bad, right? Technically, this should be h of the element x comma y. Really, I should have double parentheses here, but a common convention, if you are plugging an ordered pair into a function, is to suppress one of the parentheses. So this, by this I mean plug in the ordered pair xy into the function h. And I want you to determine if these functions are injective or surjective or bijective indeed. Okay. Now, maybe you want an example, so let me talk about the first function. The nice thing about this function is that the domain and codomain are both finite sets. There's only 5 elements, and I can figure out exactly where each element goes. Right? So what does this function do? F of 0 equals 0. That's what 0 squared is. F of 1 equals 1. F of 2 is 2 squared, that's 4. F of 3, that's 3 squared, that's 9, but modulo 5, that's 4. And f of 4 is 16, which is 1. Okay, so what this function does is it just takes the numbers 0 through 4, it squares them, and it takes the result modulo 5. And so we can see that this function is not injective and it's not surjective. It's not injective because f of 1 equals f of 4, so it's not injective. And it's not surjective because you can never get 2 as the output of this function. There does not exist an x in Z5 such that f of x equals 2, so it's not surjective. Okay, what about x cubed? Again, from Z5 to Z5, the nice thing is that the domain and the codomain are finite sets. So we can just enumerate all the possibilities for this function. We can write down exactly what this function does to every single element, which, again, if you didn't do it before, pause the video now and just try it for yourself and figure out whether or not you think it's injective or surjective or both or neither. Okay, trusting that you pause the video. G of 0, that's 0 cubed, that's 0. G of 1, that's 1 cubed, that's 1. G of 2, that's 2 cubed, that's 8, so really it's 3. G of 3 is 3 cubed, that's 27, so really that's 2. And G of 4, that's 4 cubed, that's 64, that's 4. So, is this function injective? Yes, every input maps to a distinct output. It is injective because if you take 2 different inputs, you always get different outputs. It's also surjective because every single number appears as an output, 0, 1, 2, 3, 4. Which also means that it's bijective because it's both injective and surjective. Okay, but now for the more interesting question, which is, what about this function h? Is this injective? Is it surjective? How the heck can we even tell? And I'm out of time here, right? So really, I will tell you next time how to analyze this function. But perhaps you can try to understand it before next time. But I don't want to go over 50 minutes. That would be really rude of me. So think about how to prove I mean, first of all, figure out if it's injective or it's surjective, and then think about how to prove if it's injective or surjective. Okay, next time. But since you are, bright, curious, young human beings, you want to figure out before next time. So I encourage you to try to figure out before next time. Okay, so what do we do today? We talked about the Cartesian product representation of a function. Then we talked about injective functions. These are functions that never send two different things to the same thing. Surjective functions, which hit everything in the codomain, and bijective functions, which are both injective and surjective. Okay. See you next time.